Talk about some gas laws. And when I say gas laws, there's technically like 5 or 6 of them, but we're going to start off with 3 basic ones: Boyle's, Charles, and Gay-Lussac in this. So first, remind yourself, what is a gas? Again, the gas is a bunch of particles that are spaced very far apart. Those particles might be atoms, they might be molecules. They're spaced very far apart. They're moving quickly and they collide with each other in perfectly elastic collisions, like billiard balls, where they hit and they go back and there's no loss of energy. They can just bounce around forever and ever and ever. They don't take up any space themselves. So while they move like this, their spacing is more like this. In other words, the diameter of the particle itself is much smaller than the distance between 2 particles. In fact, if we're talking about an ideal gas, there is no diameter to it. It takes up no space. Of course, that's impossible, but the idea is that it's so incredibly small that we can say effectively no volume to the particle itself, so all of the space is just emptiness. So again, talking about these first 3 laws, we have the Gay-Lussac, Charles, and Boyle's. And each of them are focusing on 2 properties of gases. So the implied, it's not stated here, but when we talk about pressure is proportional to temperature, it's implying that the volume is not changing, or the number of moles is not changing. I have like a fixed sample and I can't add more atoms or take any away. So pressure is proportional to temperature. Most of you are used to seeing it in this form. So if I divided both sides by temperature, and since it's a constant, I can pick any 2 sets of conditions, and the pressure divided by the temperature is equal to the pressure divided by the temperature in another set of conditions, as long as the volume is not changing. So this law is called Gay-Lussac. If temperature is lowered, so is volume. This is the Charles's law. Again, it's implied that pressure is staying constant and it's not changing. So volume is proportional to temperature. They do the same thing. This would be normally how it's written. V1 over T1 equals V2 over T2. The volume divided by the temperature at one set of conditions is equal to the volume divided by the temperature at another set of conditions. Now it's important that we use absolute temperature. We use Kelvin scale when doing any gas laws. It will not be true if you divide by Celsius, so it's important that you use Kelvin temperatures for all of your temperatures. The final one is Boyle's law, which is that if volume is lowered, the pressure is actually raised. So we see that pressure is inversely proportional to volume. And so if we rearrange this, we get P1V1 equals P2V2. So the pressure times the volume at one set of conditions is equal to the pressure times the volume at another set of conditions. And again, if one of them changes and decreases, the other one has to increase. We'll talk about those, how to manipulate the mathematical relationships a little bit later. I will say that then we can take all 3 of those together and come up with a 4th law that we call the combined gas law. It's basically saying, well, you don't necessarily have to keep anything constant, so that you can have the pressure times the volume divided by the temperature is equal to the pressure times the volume times another temperature divided by the other temperature at the other set of conditions. Notice that if you take this, and if volume is constant, then V1 equals T2 and it cancels out and you get another equation. That's what I'm showing you here. So if I take the combined gas law, it really gives you the other 3 laws. It won't tell you the name of them, but it sort of implies. So if temperature is constant, then T1 and T2 are the same and they cancel out and I end up with Boyle's law. If pressure is constant, then I end up with Charles's law. And if volume is constant, the pressure is canceled out and I'm left with Gay-Lussac law. By the way, this is assuming that I'm not changing the number of particles. I have a sample, a closed sample, so I'm not allowing any particles to come in or any to leave. So the number of moles are held constant. It's implied here. Just kind of reminding you too that we do have a standard temperature and pressure, so sometimes you'll see reference to STP. And STP just means a standard temperature and pressure that's a reasonable set of conditions. The standard temperature is 0 degrees Celsius. In Kelvin, again, we're going to use Kelvin for all of our gas laws, so that's 273. And the standard pressure is 1 atmosphere. We're going to commonly use atmospheres when we're doing our calculations. However, you can use, as long as you're keeping consistent with your pressure units, you can use alternate pressure units. Remember that 1 atmosphere is 760 torr or 760 millimeters of mercury. One of the things that's really powerful about understanding these equations is understanding how to sort of get some general predictions about how gases are going to behave from looking at a mathematical relationship. So mathematically, when I have a relationship like y is equal to k, where k is the constant, times x, that means that when x increases, y is going to increase proportionally. The proportional factor is this k. We can also write this as y is proportional to x. It looks like a sideways 8, or, little half of an 8. The other type of common relationship we'll see in chemistry is what we call inversely proportional. So y is equal to k times the inverse of x, 1 over x. And in this case, when x increases, then y over 1 over x, the inverse of x, decreases. So the pressure would decrease, right? As x gets bigger and bigger, 1 over x gets to be a smaller and smaller value, and so the whatever is proportional would be decreasing. So we see an opposite type of behavior. X increases, y decreases if we have an inversely proportional relationship. Sometimes this is written as y is inversely proportional. Y is proportional to the inverse of x. Over here we're talking about our gas laws specifically. Again, if I kind of rearrange in terms of pressure or volume, and I take my combined gas law and kind of rearrange it, the constant would be whatever the pressure times the volume divided by the temperature is. So, but who cares? It's a constant. So I see that pressure and temperature are directly proportional. So it looks like y and x, right? Whereas pressure and volume are inversely proportional. It looks like y and this 1 over x. So 1 over volume would be, so again, I'd only be changing one at a time. So pressure and temperature are directly proportional. Pressure and volume are inversely proportional. Volume and temperature are directly proportional. Again, I've rearranged this. So what we're saying is if I can kind of look at this and sort of see, if I have things on different sides, the equal sides, and they're both on the top of fractions, then they're directly proportional. If a variable is on one side in the numerator and one is on the other side in the denominator, they're inversely proportional, and I know they're going to kind of do opposing things when they change. And that's a very helpful sort of mindset. So I don't have to plug numbers in a lot of questions. There's a lot of questions where it simply says, if you double the pressure, what will happen to the volume? Well, if I understand that pressure and volume are inversely proportional, I know that the volumes, if you double the pressure, the volume will cut in half. So I can quickly do things without actually getting into setting up and doing math because I understand the mathematical relationships. And that's pretty powerful. So again, if there's a lot of questions that look like this. What happens to the pressure when the temperature decreases? Again, pressure and temperature are directly proportional, so it's going to decrease. What happens to the volume when the temperature increases? So volume and temperature are directly proportional. So if the temperature increases, so will the volume. What happens to the pressure when the volume increases? Well, pressure and volume are inversely proportional. So if the volume increases, the pressure is going to decrease by the inverse of the volume. So I have general relationship power off of these problems in class, but I want you to take a minute to kind of write these down and maybe try them on your own. And here's another one.